Okay, very good afternoon, everyone. Uh, it's time now, so I think we should start today's session and then more people may join further. So, welcome to this interactive session. It's the seventh session, and this is the session for NPTEL course Solid State Physics. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a TA for this course. My name is Mrinalini. I am a PMRF Research Scholar from School of Physics, University of Hyderabad. For people who are new, this is the session we have every Saturday from 3 p.m. to 5 p.m., where we discuss some topics based on the lecture videos posted in that week, and also we do a lot of lot of numerical problems related to that week's topic, so that it will help you people attempt your assignments and exam if you're taking up at the end. So first, let's have a recap of what were the things that were discussed in last week's lecture. Yeah, these are the list of recommended books you can refer to as far as this course is concerned. These will be helpful. Yeah, so last week we were discussing about Brilliant Zone, and just yeah. Last week we were discussing what is Brilliant Zone and how to construct one. Like here, for example, I had shown how we can do for 2D, that if this is reciprocal space and these points that you see are reciprocal lattices, then taking any one of them as origin, how we can construct Brilliant Zone and what we mean by Brilliant Zone. Like here, this blue square is first Brilliant Zone, and then these yellow shaded 4 triangles together are second Brilliant Zone, and further we can construct more. So this was about Brilliant Zone that we were discussing last time. After that, we went to another topic, which was about when we carry out the XRD experiment, then we see 2 theta versus intensity graph or data that we get, and we see that we see some sort of peaks there. So these peaks gives us a lot of information about the type of material whose XRD we are taking. So these intensities, especially because we know 2 theta depends on D. We have Bragg's law, 2D sine theta is equal to n lambda. For particular lambda and n of any order when we take, depending on what that HKL planes, because there are different planes in a unit cell, corresponding to that particular HKL, what is the interplanar spacing, that will result in where at 2 theta we will get peak. But what about the intensity of these peaks? So intensity depends on various factors, actually many factors, but the 2 important one were, first was multiplicity factor, which was telling us that how much intense the peak will means how many how many X-ray that is reaching, that is incident on our sample, are diffracting from that HKL plane. The more number of diffraction is happening from that HKL plane, the higher will be the intensity of that peak. And why some HKL planes intensity is more than other, that is because, as we had seen, if I have a family of 100 plane for a cubic unit cell, then this has the family has about, I think, 12 planes, 100 0 10 0 1 bar 0 1 bar 0, like in this way there are 12 planes, I think. So there are 12 planes this representing this family of plane. So 12 times more intensity we'll get from this, whereas if I have 111 family, it has 6 members in its family, I think. So intensity from this will be less. So the one factor that influences the intensity of the peaks we are getting is multiplicity. The second factor, important factor that we had discussed, was structure factor. Again, it was there's formula where is dependence on. It is something like there's form factor that depends on which element it is, because the elements with higher atomic number have more form factor and thus their intensity is more. That's why sometimes lighter atoms, it's a little difficult to do XRD on lighter atoms. I mean, the diffraction or the intensity is less. Apart from the form factor, we have e to the power minus I, and then hx plus ky plus lz. This kind of uh, formula is there. XYZ is position of the atoms in the unit cell, and HKL is that particular plane. So when we expand these summation, we get some particular rules for simple cubic, FCC and BCC lattices, which tells us that which kind of planes may give us diffraction. Like for simple cubic, when we expand this and figure out all the values, we see that for any HKL plane will result in diffraction. It will satisfy Bragg condition, and we'll see all kind of we'll see peaks corresponding to all HKL planes if it's a simple cubic. But in FCC, where the position of atoms is not only on the corner but also on the faces of the unit cells, it results in such combination that there we find a specific rule that for FCC, if HKL, these individual values, if they are all odd or all even values, means all this HKL all are odd or all are even, then only it will be satisfy Bragg's condition, and we'll see we'll see diffraction peak. Otherwise, if this is mixture means like 1, 2, 0 plane. This is odd, this is even, this is even. So this plane we'll not see if it's FCC. Okay, what we'll see? We'll see 200, 113, such things. So this is the rule we get from this expansion of structure factor formula. And similarly, there was a rule for BCC as well, that for this, the sum of H plus K plus L should be even. If this sum of H plus K plus L comes out to be odd, then we'll not get diffraction from that plane. This was for BCC. So this was also one factor affecting how the intensity will change. So these were the two important. Other things like temperature and other factors are not that important, but they also have their percentage of influence. Okay, these were the things on crystal structure. After this, we had moved on. After this, actually, we had moved on to discussing electrical properties of matter. After this, we had started discussing electrical properties of matter. So before this, we was discussing structural properties. Then we moved to electrical properties, and how we have some materials which are considered conductors, then some are insulators, and some are semiconductors. So what are their properties? And then we were focusing on metals, that metals have atoms, but the valence electron is like a moving freely, like we see in a gas, that all atoms, all the gaseous atoms are non-interacting and free to move around. The similar way, electrons in metal are free to move around and not restrict, the valence electron are not restricted to the atom. So the same model used on gas was put on metals, and there were some formulas derived. Some were able to satisfy what we see experimentally, but few properties what we see were not answered by this model. So this model we were calling free electron gas model or Drude model. Based on this, we had seen some formulas like for mean free path, relaxation time, then current density, which is the product of electron density, drift velocity, and charge of electron. Then we had seen further, after this we density of state was discussed, that it is the number of states available for occupation by electrons per unit energy. Density of states. And we had summarized that for zero dimension, the density of state depends on energy as delta function. And the graph looks like this. If this is density of state, this is energy. And for 1D, it is exponential decay. Density of state proportional to e to the power minus half. For 2D, density of state is independent of energy. And for 3D, when we derive, we see that the graph goes like this parabola kind of. So density of state in 3D. This was about density of states. And till now we were discussing electrical properties. Now further taking the electrical properties forward, there is another concept which gives us the reason why we have band of energies and why we have gaps. Like we usually, when we say that we have a metal object, then what we mean is, and what we say, how we sometimes even define metals. Metals have very small resistivity, very high conductivity, and then the gap between conduction band and valence band is very small. This energy band gap, if this is energy, then energy, the gap between the valence band, conduction band, valence band is very small, or sometimes even overlapping. Then it's metal. When the gap is very large, it is insulator. So what is this conduction? What are these bands that we are referring? What kind of bands these are? So actually these are bands of energy levels. And why we call them bands is what happened. If you remember, when we discussed potential well, that an electron is there in a potential well. So because of localization of electron restricted in this dimension, say A, when this localization of particle happens, then the energy level becomes discrete, right? Otherwise its energy will be, this is its energy, or if n or k vector, k square h bar square by 2m. But in general, but when it this localization happens, the energy levels split up into, it doesn't remain continuous, but it gets it takes discrete value. So electrons can only be in this state or this state or this state likewise. So what happens when this energy, the distance between energy levels at some point, when it's very close to each other, they are so close that they look kind of continuous, and thus they look means, I mean, we are not able to see. These are all just a way to say that energy level I'm drawing by a line. It's not like actually in solid there is a state, kind of what I mean, some ceiling on which the electron is going and taking that energy level. It is just a way to represent that this is the energy level. So instead of saying energy level E1, E2, E3, we show that this energy level is higher, this energy level is even higher. So this is just way of representing. So when the energy levels are very close, it represents something like a band, and that is what happens when we say conduction band, valence band. They are actually a lot of very closely spaced, means very with energy levels with very small difference are there, similar way here. So instead of a bunch of energy levels, we just say band, conduction band, valence band. So this band theory of solids, we'll see how we get this. We'll try to see how we can get it. It's to see its origin from the potential well kind of problem that we had many times seen in quantum mechanics. And further, it also, when joined with various models given by various researchers, then we are able to quantize how the conduction band values will be, how many electrons can take that level, and how we get how many electrons will be in valence band, and that will result if it's a metal or something. So first let's see this to understand how we get this, how this situation arises, that there is some there is some energy level existing and then there is some gap. Okay, so moving on to this. So if we are talking about a solid, especially metal, okay, so in a metal we know, just now I said that we have atoms like this with valence electron, but the electrons are loosely bound to its atom, so it's like it's free to be roaming around everywhere, but inside the material itself. It doesn't have sufficient energy to leave the metal or that body altogether. So although it's not restricted to be part of its atom, it can roam around, but it would be inside this material only. Okay, so this situation is something like a potential well, where if, let me first draw. Okay, so for a metal, this is situation what the electrons see, because if I have a metallic solid, these are my atoms, 3 atoms. Okay, if the electron, if I'm considering it, it's localized, means it's restricted to be about this electron, this atom only, then localization means the potential well, its potential energy, its movement is restricted in this position within this A dimension, and then its energy level will be discrete. These things we know. Okay, similarly there is another electron, if we only consider for time being 3 electrons, but we know they are like 10 of 10, like 10 to the power 10 and so on, many more, but we are just considering here these. So if this is the situation, I am drawing only 3. So for all, this will be the same situation. But we know that is not the case. And only, so we are talking about valence electrons which are free to move. Apart from valence, whatever the, like, say, like, if I have carbon, not carbon is not a good example, I mean some metallic atom, so inner shell electrons will be bound. For that, this situation is valid, but the valence electron will be free to move around. For that, the potential energy is higher, I mean, and the electrons which are completely out of the metal, if they go, then their potential energy will be 0. So the potential energy is like this. This is for the, we can say these are nearly free electrons, because they are not localized to one particular atom, and they are not completely free also, because when they will be free, they will be completely out of this material, and then their potential energy will be 0. Right now there are some negative here. So these are nearly free electrons, and the one completely localized to their atoms will be bound electrons. So we have 3 types of electrons: one completely free, nearly free, and then bound electrons. This will be the situation whenever we have a metal atom in simple way. Here we know one atom's radius is about, in usually in angstroms, so that means this is about 10 to the power minus 10 meter, or 1 angstrom. Okay, whereas this dimension, if I'm talking about the whole metal where the nearly free electrons are can move around, this length let's call L, and let's take, I have a 1 meter big material, then nearly free electron is free to move around in all this 1 meter dimension, whereas these bound electrons which are localized to their atom can only move in this very small region, 1 angstrom. Okay, this is another thing. So now for free electron, we have, I told we have 3 type of electron cases here: free electron, nearly free, and bound electrons. So for nearly free, for free electrons, the energy is given by h bar square k squared by 2m, where k is the wave vector of this electron. Wave vector of this electron. Whereas for nearly free electron, energy, and k has all possible values. Whereas for nearly free electron, in this case, energy will, the formula will be this, but now the k value can only be n pi by L, right? N is the integer, the positive whole number actually. And for bound electrons, energy will be dependent on wave vector, where wave vector can only take values n pi by A, because here the dimension is A and here the dimension was L, and L is of course more than A. So this is the situation, this is how the energy will vary for these 3 different categories of electrons. As far as these 2 are inside the solid, this is not, but just I am presenting comparison, where when we have free electron, which will be not inside the solid material, the energy is continuous. If I draw it in a graph, okay, then this is energy, this is versus wave vector, then because, sorry, this will be actually, should not cross, this will is better because the its E is proportional to k square. For free electron, this is the energy depends on wave vector with and represent this is dependence is parabolic. Whereas for nearly free electrons, again the E versus K diagram is now how it changes is, here I told that all the possible values of K is valid, whereas when we have nearly free electrons, energy values are only those energy values are possible where K is n pi by L, means pi by L, 2 pi by L, 3 pi by L, and so on. So that means only those energy values are possible when K is pi by L, 2 pi by L, 3 pi by L, and similarly minus pi by L, minus 2 pi by L, minus 3 pi by L. So it could be something like this will be corresponding to this. Okay, similar way this side. So if you closely see, this is also following the parabolic path, because here also A is still proportional to k square, but k cannot take all the values. For nearly free electron, k cannot take all the values, it can only take where L is integer. With this Z like this, we represent integers. And these are those possible energy values. Whereas here, all possible energy values were possible. Now the third case is of, this was first, this was for nearly free electron. Third is bound electron, which was here. These. So for bound electrons, again, it will be similar to the situation for nearly free electrons when we graph E versus K. Now the energy is still proportional to k square, but here k can only take n pi by A, and so the values it can take is pi by A, 2 pi by A, minus pi by A, minus 2 pi by A, and so on. Again, this will be, but these two will not be same. Why? Because this A and L are very different. L has a dimension of like in meters, right? So this K value will be smaller, whereas here A is angstrom, means this K value will be larger. So that is the difference. There is huge difference in the scaling. So this is how it's known that energy depends on wave vector of electron. If the electron is free, then the energy, it can take any value of energy, whereas as it becomes nearly bound or completely bound, energy becomes discrete, and this is what we are showing here. Now what happens? How do we get to see the energy band? Let's move towards that. So when, if you remember, we had this just now we discussed about Brillouin zone. Okay, just now we're discussing about Brillouin zone. I think we'll come to that. Okay, so in 1D, let's now discuss this origin of bands in 1D, because 3D is difficult, and even 2D we don't need to go to 2D. First, let's only stick to 1D, where our lattice constant or the lattice vector will be A. This is the parameter which we which we repeat, and we'll get the whole 1D lattice crystal. So in 1D we have lattice constant A. So in reciprocal space, because every real space we can have corresponding reciprocal space. So for this 1D real space, reciprocal space, its reciprocal vector will be 2 pi by A, right? We have this 2 pi constant. Like if you remember, we were trying to find how to find the reciprocal vector, and we had seen either when we ignore this constant, then it's 1 over volume, and if we are trying to find A star, then it will be 1 over volume and B cross C. But when we consider this constant, it is 2 pi and this. Okay. This reciprocal space, or also called K space, especially when we consider K space, this 2 pi factor comes in the picture. Okay, so this is real space vector, this is reciprocal space reciprocal vector. So if this is the situation, then if I draw reciprocal space with reciprocal lattice points, the way we had seen here, this was reciprocal space and 2D case, and these were all reciprocal lattices in x and y direction, or x prime y prime direction. Similarly here for 1D, when I am drawing reciprocal lattice points, this is then, and they will keep on extending. Of course, I'm only drawing few of them. Any one of this lattice point I can consider origin. Let's say this I would take as origin point. Then the next lattice vector, from this origin, when I draw the lattice vector, the next point will be 2 pi by A, and this side it will be minus 2 pi by A. Then next will be 4 pi by A, and similar will be these lattice points are at can be represented by the lattice vector correspondingly. Like if this is the origin, then this is 2 pi by A, this is minus 2 pi by A, this is 4 pi by A, this is minus 4 pi by A, and so on both directions. If I change my origin, if I take this as my origin, then this will be minus 2 pi by A, and this will be plus 2 pi by A. But we know there is symmetry in real space and reciprocal space, so any point can be taken as origin, and this we can get the corresponding neighboring vectors, reciprocal vectors we can get. Because in real space also we used to do the same thing, right? Like if it was 1D, then if I'm considering this origin, and this is A, and this is 2A, or if it's 2D, then we used to have either I can have my this will be my lattice vectors A, B, which I will repeat to get all the points. This is, and similar way in reciprocal 1D space, if this is my origin, with the reciprocal vector 2 pi by A, I can generate all the reciprocal lattice points. I hope this is clear, because this is very important. We need this information. Okay, let me draw it again. So I'll try to keep okay. Taking this as origin, again this is 2 pi by A, reciprocal lattice point, this is minus 2 pi by A, this is 4 pi by A, minus 4 pi by A, 6 pi by A, minus 6 pi by A, and so on. And just to make it, like if I make them to lie on the line, just for my understanding, but they are all the same in 1D, so they are all in the one dimension. Okay, now if you remember, when we were talking about Brillouin zone, we had said we are drawing this in reciprocal space, and what this wall meant here, These points were reciprocal lattice points, and you remember the step? We first were joining the center, the origin, with the any neighboring, first the like nearest neighboring lattice point, in this case these four. After joining the origin with these lattice points using this reciprocal vector, next step was to take perpendicular bisector, which this blue line represents. So for this reciprocal lattice vector, we were drawing a perpendicular bisector, and that perpendicular bisector was the crystal plane in real space. Okay, these blue walls are all real space crystal planes. Why that information I recalled? Because now these are also reciprocal lattice points. So if I draw here uh, half of it, right? If this is my origin, I'm joining the nearest reciprocal lattice, then perpendicular bisector to it will be my crystal plane in real space. And we had also seen when we discussed the concept of Ewald sphere, then when XRD is incident on these crystal planes and there is some lattice point on it, then we get diffraction. And that was the significance of this real space, that when we try to understand the XRD pattern, then these are helpful. So here also, this is my nearest neighboring reciprocal lattice point. If I draw perpendicular bisector, means the angle is 90 degree and it's cutting this reciprocal vector into exactly half. The same way on this side, because this point is also the nearest neighboring lattice point. That means the Brillouin zone, first Brillouin zone that I was drawing in the case of a 2D here, whatever this zone is enclosed by this blue wall, blue line, that was first Brillouin zone. The same thing we are doing here. Connecting the origin with the first nearest lattice point, because this is the case of 1D, so we have only in one direction. When we draw these perpendicular bisectors, that means this is first Brillouin zone. Okay. Then we'll draw next Brillouin zone. I'll connect this origin with next reciprocal lattice, which is 4 pi by a, and we have to draw perpendicular bisector, means we have to draw a perpendicular at exactly half of it. So from 0 to 4 pi by a, half of it will be at 2 pi by a. So my next perpendicular will come at 2 pi by a. Now the third nearest neighbor, the similar way we will do on this side also. So this was the first nearest neighbor. The second nearest neighbor will be minus 4 pi by a, and half of it means here minus 2 pi by a. Okay, that means this area combined with this region, not area because it's 1D, this distance and this distance combined will give me second Brillouin zone. Okay, similar way, now my third nearest neighbor, which is 6 pi by a, half of it 3 pi by a, that means it will be here somewhere. This side also at minus 3 pi by a. This will be my third Brillouin zone. Okay, so similarly we'll get lot of these, and they all represent the real crystal planes. So if I draw, this is the wave vector, okay, if I draw how the, if I do E versus K for this situation, okay, this I'm just drawing that this is some line passing through origin and I take E. If I draw E versus K for this situation, usually E versus K for free electron is just a parabola. All the values of K is possible. But here, for this 1D case of where all these lines are crystal planes, and we know at crystal planes diffraction happens. Reciprocal lattice is imaginary concept, but these crystal planes are real thing. So diffraction happens means electrons, which are also in quantum mechanics considered as waves. So wave of electrons interact at these crystal planes, and that leads to some sort of change in the energy. So this energy, which is proportional to k square, but at every crystal plane there will be some distortion. So instead of looking like this, let's come to here. So these are for 1D. Okay, this is in reciprocal lattice point. Reciprocal lattice points in 1D. This I am taking as origin. Again, I am emphasizing this is arbitrary. I can take any point as origin. If I take this point as origin and then E versus K, this is my E. I'm taking at origin this E and versus K. Then my graph, which initially looks like this will distort. I'll tell you how it will change. Just take some other color. So it changes to something like this. Oh, difficult to, not difficult, I mean, just test this. I don't know what is its problem. If I put pressure here, some problem happens, but there's some distortion that happens. So, I mean, what is, I am not able to draw because this pen is creating problem. If what happens is, instead of going following exactly parabola, every time it encounters crystal plane, yeah, again, see, every time it encounters crystal plane, there is some distortion, like this. There's some problem my pen is having. It doesn't remain like this. I don't think it will be for some reason. The excess is gone. I don't know what is the problem this thing has. Every time the crystal plane is encountered, Instead of getting this continuous smooth curve, we see distortion like this every time the crystal plane is encountered. This I'm not able to draw properly because my pen is creating problem, but it looks something like this. Okay, and this kind of structure. So what happens is at every point there is some gap happening. So energy values are continuous here, but it's not. It's getting discontinuous here. At every whenever the crystal planes are encountered, there is some continuity is lost. That results in what we call forbidden energy gap, and the other things are continuous. So this way of representing is actually called extended zone scheme. Okay, this way of representing energy versus wave vector, where we are talking in terms of first Brillouin zone, second Brillouin zone, third Brillouin zone. This representation is called extended zone scheme. And let me try again. I'm not sure, it's not letting me draw properly. Basically, it's not continuous as soon as the wave vector encounters these crystal planes, and because of that, we see a gap. Right now, it's working for some reason. So when you see, we see this, and every time this is continuous or discontinuous, corresponding to every this energy I am taking, because this axis was energy axis, right? And this was K. So corresponding to everywhere where it's becoming discontinuous, when we draw this, we'll see that it's like a all the values in this are continuous. I mean possible. Sorry. These are actually not the gap. Sorry. Let's draw this side. So from here, because my pen is creating problem, but so all till here to here values are allowed, and then there is some gap when it comes here. So this is allowed, here also it's allowed, and then this much is, this is gap. I'm drawing here means it's like I'm telling you this energy level. This is all allowed energy levels, levels. Then here also all these are allowed energy values. All are allowed energy levels, and then in between this gap that we see, this is what we call forbidden energy gap. So this is how what I wanted to basically represent is, or trying for you guys to understand, that if I have a completely free electron, if I have this was just Brillouin's own thing, but if I have completely free electron, then for it my energy was h power square k square by 2m, where k is the wave vector of electron. But if it faces any kind of localization, then this k cannot take all values, and that means not all values of energy are possible for that electron when any kind of localization happens. And this kind localization we see when we have metals inside, when we have electrons inside metal body, right? Because when that happens, our electron, which is not free anymore, it is we have electrons which are completely bound to the atoms, which are in like innermost electrons, and then we have valence electrons which are free to move around. So valence electrons, since they are free to move around and they are not localized to their atoms, have can be called nearly free electrons, and the electrons which are inertial electrons and are completely bound to their atoms have are called bound electrons, and for them k value can only take specific values, and thus their energy levels are also not continuous but discrete. So that's why when we are discussing about metals, the E versus K, which for free electron is continuous, but when we have these bound or nearly free electrons, the parabolic dependence that we see for E versus K, it's not continuous anymore. Every time these crystal planes are encountered by the electron wave vector, there is discontinuity, and that's how we get energy bands and a forbidden gap between those energy bands. Otherwise, if this red curve, which is representing the energy versus K relationship for free electron, we see all values are possible here. That means it's like all values of energy is possible. But because of localization, there is change in this relationship because only discrete values 2 pi by a, 4 pi by a, 6 pi by a corresponding to reciprocal lattice points, here they face distortion, and thus we have only these energy levels possible, and that is how we get bands in our metals, okay, in our solids. But this was specific case. Okay. And this picture, this way of representing the energy levels in solids, this we call flat band diagram. Flat band diagram. Okay. And then if we talk about Brillouin zone, so already I told you, like in 2D reciprocal lattice, we had seen that this is first Brillouin zone, this is all these four together is second Brillouin zone, and further if we construct, we'll see more. Similar way here, we were seeing that the area enclosed by first crystal plane, this is first Brillouin zone, then the region between next this is, yeah, the region between next crystal plane, this and this together will constitute second Brillouin zone, and then this and this will be third Brillouin zone, and so on and so forth. So that was another thing. So here we'll have, if I say my first Brillouin zone is from minus pi by a to plus pi by a, and my second Brillouin zone is minus 2 pi by a to, this was a crystal plane I had constructed at perpendicular bisector, right? That means this was minus pi by a. This was also plus pi by a. Minus 2 pi by a to plus pi by a, and pi by a to 2 pi by a together is second Brillouin zone. So similarly, and this is how we get energy bands in our solids, and here we specifically were seeing for metals. So this is how we define metals, that in metals, when we say we have conduction band, that is actually a bunch of lot of energy levels very closely spaced, and then we have another which we call valence band. Okay, that is also set of very close energy levels, and it's not like sometimes we mistake, we think that there are only these two bands, one is valence, one is conduction band, but that is not the case. As we saw here, we have a lot of these bunch of energy levels, means lot of these bands, and only what matters is uh, we'll call it, okay, like if I have a situation like this, that I have a band completely empty. Empty means energy level is there, of course. Energy levels are there, but not occupied by electrons presently. Not occupied by electrons. Okay, so usually we represent this in, so I'm, for clarity I'm telling you that when I'm saying band, band means this energy band. When we say this word, it means kind of not scientific definition, but for you, for your clarity, it's like bunch of energy levels, all the possible energy levels. So they are very closely spaced. That's why I'm drawing like this. But usually when it's that energy level or energy band is not occupied by electron, we simply represent it as empty. When we show it's empty means it's not occupied. Okay. So if we have a situation like this, and then I have another, usually as higher we go in energy, the this increases, number of the band width increases. So the lower one should be a little smaller. Okay. And let's say this is completely filled. Of course, not only energy level I'm showing, let's say this is completely filled. So that time we shaded bands means it's filled, and unshaded means empty. So although I was telling you this by this line, I was representing energy levels, but usually we don't show them, and we just understand it's like by default that when we refer to energy band means of course there are energy levels, but to represent occupied and unoccupied energy band, we shade them, and this shaded means it's occupied, this unshaded means it's not occupied. So when we have energy bands like this, then we further can have more all occupied like this. So what I was emphasizing, it's not like we have only two bands, conduction and valence. We have lot of other bands also. But we are interested just to see usually between the unoccupied and occupied, wherever it's. We don't bother about already, or maybe they are more unoccupied and they are more occupied this side, but that we don't is not we are not concerned when we want to define electrical properties of solid. That time we only want to see, focus on the region where there is some occupancy of electrons and some levels are empty. So what happens when this topmost occupied energy level, which we know is called Fermi energy level. Fermi energy level we call the level up to which the levels are completely filled. So the top of energy occupied energy level and the bottom or the lowest of unoccupied energy level, when the gap between them is more than 2 electron volt, then we call that that material or that solid as insulator. Okay, and when this energy band gap, which we also represent at Eg, when this is less than 2 electron volt, we call it semiconductor. Okay, why? Although it may seem a very small value, but it's not the case, because if I tell you room temperature, like usually we take room temperature is about, like we can take 30 degrees centigrade or something. In Kelvin it will be 300 Kelvin approximate, and this room temperature, this thermal energy If I convert it into electron volt, then this thermal energy will correspond to about 25 or 26 milli electron volt. So room temperature thermal energy is in the order of milli electron volt. That means if I have to supply, you can imagine now in comparison with room temperature how much more temperature or energy is required to excite the electrons from this occupied levels to this unoccupied levels for conduction to start. Because if this is the situation that at room temperature the energy is only in milli electron volt, then you can see 2 electron volt is such a high value. That means a lot of energy is to be applied for electron to excite from valence band to conduction band. That's why we say this material is not some material we say, right, it's insulator, means conduction is very less, resistivity is high, because to make it to conduct we need to apply very large field, large voltage, or we have to supply very high temperature or somehow to excite the electrons. So that is why we say when the energy gap between the topmost occupied level and lowest most unoccupied level, which we just generally call conduction band and valence band, when the energy band gap is less than 2 electron volt, we can call it semiconductor. Means intermediate, its properties of conduction is intermediate between insulator and metal. But if the energy band gap value is more than 2 electron volt, then we call it insulator. It doesn't need to be exact, but this is like usually we take. And then what happens for metals? For metals, sometimes what happens is, if, as I said, we have a lot of many energy bands, so on, maybe depends on what kind of atomic number it is, because the higher the atomic number, the more number of electrons are there. So anyway, so in case of metals, what may happen, that all these are filled, maybe all these are filled, and this one is also half filled. Okay, then so what I wanted to say, energy band gap is not only like, in this case the occupied level was till here, so they need to overcome this energy band gap for conduction. But in metals, what is seen is the lowest occupied level and the unoccupied levels are, because this all is unoccupied, right, and this is the Fermi energy, the topmost occupied level. It can easily excite and go to unoccupied level. That's why in metals the conductivity is very high. It's very easy to for the electrons in metals to start conducting. Also another case, in metals, sometimes it happens that the conduction band or the unoccupied band and the Fermi band, valence band, that is the occupied band, they overlap. And in this situation, here you see the lowest of the conduction band and the topmost of the valence band, this is higher than this, so it can easily go to the conduction band. This is the situation that we see in metals. And these conduction band, what is the forbidden energy gap, how many levels are there, all these things depend on type of material, how many number of electrons are there in that material. So depending on that, we'll get some change in this curve, and that will influence how my energy band gap picture I get. So I hope this was something understandable. And then further, so this was just visualization for visual understanding how we get the picture of energy bands and how we get gap. But further, this picture, when we connect with a model called Kronig-Penney model, then in quantity we get how many levels are possible in the energy bands and what are the this energy band gap. In this gives us quantification of energy band theory. And there also, that's why we begin with assuming that we know that all on the atoms, the electrons feel more attraction. So we draw potential energy well like this. This represents all the ionic position, and far away from there, electron's potential increases. And this is how we take a start, and we do derivation, which is done in the this week's lecture videos. So you can see the derivation there. So I was just trying to give you picture, and for quantification of these energy levels and band gap concept, Kronig-Penney model kind of gives better answer. So this was about band theory of solids, how it comes. And I think now we can start doing some problems based on this. I have seen you guys, I think, sorry, I was not part of that discussion forum. I saw it just a few days back, and so I started answering some of the questions. I think there is one more TA for this session, I mean, interactive sessions, but I came across those questions which were posted on the discussion forum, so I've answered few. But in case if you guys have questions, that's why I would say you can come to these sessions when they are live and ask your doubts. That would be better, because not everything is quite easy to explain in through texts or mails. Okay, anyway, let's move on to the first question. So, okay, so first question is, find the energy level in sodium for which the probability of occupation at 300 Kelvin is 0.75. Means probability of occupation is 0. I can change back to red actually, that is better contrast. Probability of occupation of Fermi energy level 0.75. Fermi energy of sodium is 3.13 electron volt. Okay, we have to find energy level, okay, for which the probability of occupation at 300 Kelvin is this. So formula is, probability of occupation is given by 1 over 1 plus e to the power E minus EF by kBT. Okay, here we have to find energy level. Fermi energy is given. So we'll rearrange this equation, and this will become E minus EF by kBT is equal to 1 over P. Then further E minus EF by kBT 1 over P. This 1 I will bring to right hand side, and it will be 1 by P minus 1. And to remove this exponent, we will take log on both sides, natural log. Then this will be, because natural log of e to the power x is x. Okay, so this will be E minus EF by kBT, and on this side it will be e to the power, natural log of 1 by P minus 1. Further, I need to find out E. So this denominator I'll send right side. It will be kB times T, natural log 1 by P minus 1. And here it will be E minus EF. Okay. Slide. Okay. Then E will be EF plus kBT multiplied by natural log of 1 by P minus 1. So energy I need to find out. EF is given to be 3.13 electron volt. 3.13 electron volt plus this kBT. Kb is 1.38 times 10 to the power minus 23. Okay, this is interesting. This is in electron volt, whereas kb is in joule. Okay, let me write electron volt here. kb is 1.38 times 10 to the power minus 23 joule per Kelvin multiplied by 300 Kelvin, and this whole thing will be a constant, and this has because this was joule per Kelvin multiplied by 300 Kelvin, that means Kelvin is gone. Now this portion has unit of joules, whereas this EF has unit of electron volt. We need to make them same for calculation properly, whereas meanwhile this will be 1 over P. P is 0.75 minus 1. First let's calculate. Okay, I need to convert this also. So what happens, the relationship between joule and electron, like one electron volt is, yeah, so actually 1 electron volt is 1.6 times 10 to the power minus 19 joule, and answers are in electron volt. Okay, so I need to keep everything in electron volt. That means I need to convert this joule into electron volt, and that means 1 joule will be 1 divided by 1.6 times 10 to the power minus 19 electron volt is 1 joule. So I need to convert this. So taking care of this energy will become 3.13 electron volt plus 1.38 times 10 to the power minus 23 multiplied by 300 multiplied by this, because I want to convert this joule into electron volt. 1.6 times 10 to the power minus 19 multiplied by this natural log, and inside it will be 1 minus 0.75 means 0.25 divided by 0.75. Yeah, anyway, I mean, just have to be 1 by 3. Natural log of 1 by 3, the value, okay, so this will be 3.13. Then we will calculate this with this. 1 point. Natural log of 1 by 3, this will be minus 1.098, 3.13, and this will be 1.38 multiplied by 300 divided by 1.6 is 258.75, and all the powers, this will be 10 to the power minus 23 plus 19, and this multiplied by minus 1.098. Further, do this. Minus 23 plus 19 minus 23 plus 19 means minus 4, and when we will calculate this, the final answer is 2.13 0.025875 multiplied by minus 1.098. When we calculate this, the answer will be 3.13 plus this will be minus 0.03. Answer will be 3.10 electron volt. So this is the 3.10 electron volt is the correct answer. Okay, next question. Find the temperature at which there is a 1% probability that electron in a solid will have energy 0.5 electron volt above the Fermi energy. The same formula we'll use, which is probability is 1 over e to the power e minus ef divided by kBT. Here the probability is given in percentage, so this will be 1 by 100. 1% means 1 by 100. We need to find out the temperature, means T is unknown here. When we substitute, energy is given to be 0.5. Oh, so E minus EF is given because it's given that energy is 0.5 electron above the Fermi energy. Means if this is the Fermi energy, then electron is 0.5 electron volt above Fermi energy. This increase is 0.5 electron volt, means the difference is 0.5 electron volt. Okay, and answers, okay, are in Kelvin. 0.5 electron volt or okay, let me keep it like this, E minus EF by kBT. Let's just keep. First let's resolve this exponential from here because it can make this thing difficult. So let's take reciprocal on both sides. So this side will become 100, this side will become e to the power e minus ef by kBT. Now again we have to take natural log on both sides. Natural log of 100, natural log of this, again with the same thing, using this identity. This will be e minus ef by kBT. Natural log of 100. Oh, I made mistake here. Plus 1 is also there. Sorry. Plus 1 is there. So when I take reciprocal, this is there. So natural log of 100, it's not. I have to bring it this side, then it will be 100 minus 1. So natural log of 99. Okay, natural log of 99. And then this E minus EF will be kBT multiplied by natural log of 99, or we can write this E minus EF is given 0.5 electron volt. This is 0.5 electron volt is equal to this kBT natural log of 99, and I need to convert because kB is in joule per Kelvin. So I will convert electron volt into joules, and 1 electron volt is 1.6 times 10 to the power minus 19 joules. So this will become 0.5 multiplied by 1.6 times 10 to the power minus 19 joules is equal to kB will be 1.38 times 10 to the power minus 23 joule per Kelvin multiplied by temperature, which we need to find out, and then log of 99. So now we'll just rearrange and we'll be able to find out the I should have added more slides here. Let me just do it, otherwise everything I'll have to do. It's okay. Okay. So now the temperature we'll calculate. It will be 0.5 times 1.6. 0.5 times 1.6 is 10 to the power minus 19 divided by 1.38 times 10 to the power minus 23 multiplied by natural log of 99. When we do this calculation, you get 0.5 multiplied by 1.6 divided by 1.38 divided by natural log of 99 also will be 0.126157 multiplied by 10 to the power minus 19 plus 23. This will be minus 19 plus 4. It means 1261.577 Kelvin. So the answer is this, closest is to this. This is the correct answer. So the same formula we are using in all these questions. And now the next question, the third question is the concentration of free electron in sodium. Okay, so we are given concentration of electron means number of electrons per unit volume, which we represent by the small n. Calculate the Fermi energy at 0 Kelvin. Okay. Given this is the Planck's constant. Okay, now we know that Fermi energy at any particular temperature is given by h bar square divided by 2m 3 pi r square n to the power 2 by 3. This is the formula. Here n is given and we have to find out at T is equal to 0 Kelvin. To find out the Fermi energy at 0 Kelvin, so it will become h bar square by 2m, and since we are given h, no h bar, which is called reduced Planck's constant. H is called Planck's constant, h bar is called reduced Planck's constant, and it is actually h over 2 pi. So we have to convert it into h. So it will be better if I write like h square, and this will become 4 pi square, and then this will be 3 pi square n to the power 2 by 3. This will become h square by 8 pi square m, and if I take m square outside and 3n let's say is still inside, but I take out this pi square because pi square I have to calculate here again won't be useful, so I'll take out this pi square out. So it will be pi square multiplied by 2 by 3 means pi to the power 4 by 3, and we have pi square here. That means it will be 3n to the power 2 by 3 h square divided by 8m and pi to the power 4 by 3 minus 2 means pi to the power minus 2 by 3, because 4 by 3 minus 2 is 4 minus 6 by 3 is minus 2 by 3. Yeah, this will be pi to the power h square divided by 8n pi to the power minus 2 by 3. Further when I put the values, it will be 3 times n. N is 2.5 times 10 to the power 28. 2.5 times 10 to the power 28. This whole to the power 2 by 3. And then pi to the power minus 2 by 3 means actually 8. And mass of electron we know 9.1 times 10 to the power minus 31. And then we have pi to the power minus 2 by 3, which I can write in denominator as pi to the power 2 by 3. This is the Fermi energy at 0 Kelvin. When I calculate this, I have to calculate multiplied and then take 2 to the power 3. It will become 2.5 times 3 to the power 2 by 3 to 3.83. divided by 8 multiplied by 9.1 72.8. This also, if I take into numerator, it will be plus 31. This will be pi to the power 2 by 3. Further, and get 5.023. This will be 10 to the power minus 19. 1.6 10 to the power minus 19. The conversion, because it's in joule second, my answer is in electron volt, so I need to convert this, and then my final answer will be 3.13 electron volt. So option C is the correct answer. Okay, now next question. Concentration of free electron density means this electron density. This is given 2.5 times 10 to the power 28 per meter cube. It's like number of electrons per unit volume. Calculate the Fermi velocity. Okay, this time we need to calculate the velocity. We know if we have to calculate the energy, just now we used Fermi energy formula, and energy we can relate to momentum and thus the velocity. So if I find out the energy, then my life will become easier. So what is the relation between energy and all the information given to us? The same formula. Energy will be, the Fermi energy will be equal to h bar square. Why is it given h bar? Oh, it's h bar square divided by 2m multiplied by 3 pi square n to the power n to the power 2 by 3. Now I don't need to find energy, but I need to find the Fermi velocity. Now we know energy or indirectly could have done this way. So we know momentum is mass times velocity, and here since Fermi velocity, so this is the relation. Now also we know this is equal to h bar kf, where kf is the wave vector. So from here we can see that Vf will be, which I need to find out, it will be, so I don't need to include this directly. I know these two relations for momentum. One is mass times velocity, another is this wave vector multiplied by reduced Planck's constant. So using this equation, I can find that Vf is h bar kf divided by n. And I'll use this directly, which will be h bar n, and kf is 3 pi square n. This is direct formula. Again, h bar is h over 2 pi, so this will be h over 2 pi m, and this pi square outside means pi to the power 2 by 3, and 3n inside. When we substitute all the values, this will be 6.64 times 10 to the power minus 34 joule second, pi to the power 2 by 3, 3 multiplied by n, which is 2.5 times 10 to the power 28 per meter cube. In the denominator, we have 2 pi m, which is 9.1 times 10 to the power minus 31 kg. When I will calculate all that, I will get 1.05 multiplied by 10 to the power 6 meters per second. This will be the correct answer. Okay. Next question is the number of electrons per unit length of a crystal. So here we are talking about 1D. So this is again, it's like number density here. Let's see. So here instead of electrons per unit volume, it will be electrons per unit length. This will be 0.5 electrons per angstrom. The total number of electrons to accommodate on a line of 1D crystal is even number. Determine Fermi energy of the system. So for Fermi energy for 1D, the formula is h bar square divided by 2n nf pi by L whole square. Okay. So what happens is for any energy level, we know that maximum it can occupy 2 electrons, even if all its quantum numbers is same. Like if its first principal quantum number is n, only one can be spin up, one can be spin down. So mostly 2 electrons one energy level can take. And here if we have say n number of electrons, then how many energy level it can occupy? N by 2. Why? Because say if I have 2 electrons, then I can have both in one level. So if that means if I have 2 electrons, then 2 by 2 number of electrons and number of levels. If I have n number of electrons, then total n by 2 levels will be occupied. How? Because if there are 2 electrons, then 2 by 2 is equal to 1. 1 level will be occupied. If I have 4 electrons, that means 4 by 2 is equal to 2. 2 levels will be occupied, because plus half minus half, this spin will be different, and 1 level can occupy only 2 electrons. That means if I have n number of electrons, then n by 2 levels will be occupied. That means that if n is the total number of electrons to accommodate on a line, because here we are talking about line, then for even number of electrons, this Fermi level of Fermi length or number will be 2nf. Nf is the principal quantum number. Like this first principal quantum number, second principal quantum number, usually we start from down, 1, 2, 3 like that. So that many number of states will be occupied, or that the principal quantum number we can represent the n as. Okay. means like n is equal to 1, n is equal to 2, n is equal to 3. That will become our NF, the highest occupied Fermi energy level. So here when we will use for 1D the formula, which is h bar square divided by 2m nf pi by L by square. This will be h bar square divided by 2m n by 2 pi by L square to be equal to, again h bar is equal to h over 2 pi. So h bar by 4 pi square multiplied by 1 over 2m, this, and this will be n divided by 2l square. If I take out pi square, then this and this cancel. I will left with h square by 4, 8n. If I take this out also, then this will be 8, and this will be 2 square means 4, and I have m. It will be n by l square. N by L was 0.5 per angstrom, right? So this will be, EF will be, after putting all the values for H, 6.62 10 to the power minus 34 whole square, 8432, 9.1 times 10 to the power minus 31, 0.5. But this is an angstrom, I need to change it into meter. 10 to the power minus 10, and then this answer will be 2.35. We need to change it into electron volt, it seems, because the answer is in electron volt. That means I need to divide all this by 1.6 times 10 to the power minus 19. Answer will be 2.35 electron volt. To do these calculations, we are a little less on time, that's why I am rushing through. This will be the correct answer. You need to take in mind, after these calculations, you need to divide by this factor to convert. Otherwise, the answer will be in joule, and we have answers in electron volt. So that's why we need to divide by 1.6 times 10 to the power minus 19. Okay, next question. Consider silver in the metallic with one free electron per atom. Calculate the Fermi energy at 0 Kelvin. We need to calculate Fermi energy at 0 Kelvin. All the other things are given. So we know when we calculate density, because we have been given it's silver in metal with one free electron per atom, and we have been given silver density is given. Okay. So we know number of silver atoms per unit volume. Like if I know density, then it will be number of atoms multiplied by atomic weight or mass, we can call, divided by volume and Avogadro number. Here I want to find out number of not only number of atoms but number of atoms per unit volume. I want to find out electron density. So N by V will be density multiplied by Avogadro number divided by atomic weight. Okay. Now this density is given, which is 108. No, sorry. Density is 10.5 gram per cc. It is. Density of silver is 10.5 gram per cc. Okay. Other things are in SI unit. Actually, we should keep this also in SI unit, I think. In that case, gram, wait just a minute. This if I convert into kg per meter cube, then this will be 10.5 gram to kg means 10 to the power minus 3 divided by centimeter to meter 10 to the power minus 2, and because this is centimeter cube, this will be 3. When we will do this, we will get 10.5 minus 6. It will go up, means plus 6 means 3. 10.5 times 10 to the power 3 kg per meter cube. Okay, from gram per cc it will change to kg per meter cube. So this will be 10.5 times 10 to the power 3 kg per meter cube, and Avogadro number we know 6 point they have not given. Okay, 6.023 into 10 to the power 23. Atomic mass is 108. Usually I have told you many times that when atomic weight is given like this, that means it's in gram per mole. So here everything is an SI unit, means I need to change it to kg per mole. So gram to kg means 10 to the power minus 3, I'll multiply. Then it will become kg per mole. Okay, these conversions we need to keep in mind, otherwise even if our formula is correct, the answers won't be right. So when I'll calculate all this, I'll get my number of, because every atom is contributing only 1 electron. So that's why this is sufficient. And my answer will be 5.85 times 10 to the power 28 per meter cube. This will be my electron density. Now to find out the Fermi energy, at 0 Kelvin, h bar square divided by 2n, 3 pi square n to the power 2 by 3. When I will substitute n here and these other formulas, of course h bar I need to change to, it will be 4 pi square n. This pi square outside means pi 4 by 3, 3n to the power 2 by 3. Substituting values and calculating everything, the final answer I am giving you, it will be 8.8 times 10 to the power minus 19 joule. Okay, answer is again in electron volt, means I need to divide it by 1.6 times 10 to the power minus 19, and then I will get 5.5 electron volt. Please go through the calculations. Okay. Next question is, so we have atomic radius of sodium BCC is 1.86 angstrom. Calculate the Fermi energy of sodium at temperature of 0 Kelvin. Again we have to calculate Fermi energy at 0 Kelvin. Consider sodium atom gives one free electron and it's BCC. Okay, I have to calculate. Okay, to calculate this Fermi energy, I need electron density, electron per unit volume. Volume means AQ. What is A? So A, here I am given radius of BCC atom. Now for BCC atom, this was a question discussion forum also. I think many of you who have already paid attention know that I have been telling it many times, that whenever we have a unit cell, and although we tell that if it's simple cubic, all the atoms are at corners, we represent it small, but in reality they are all touching each other. They are so big that they are touching each other, but we usually don't draw it like that, otherwise I won't be able to see all the atom positions. So that's why we draw it small, but in reality they are all touching each other. This is for like simple cubic unit cell. For BCC, we have atom on the, like in the body center, means the diagonals have atoms like this. These three atoms falling on the body diagonal touch each other. That's why for BCC we can take relation. This is 1R, this is second R, this is third R, this is 4R. That is 4R is equal to, and the body diagonal, these things actually we emphasize many times, so I don't think I need to repeat it again. But for BCC, we have 4R is equal to, and the body diagonal is, if this is edge is A, then face diagonal is root 2A and body diagonal is root 3 times A. So So this is the relation. R is given. I can find out A. A will be 4R divided by root 3. 4 divided by root 3, and R is given 1.86 angstrom. Now I can calculate V, which will be A cube. Now all these things, when I will put in my Fermi energy formula, what I have to calculate here? Okay, yeah, Fermi energy, when I will put it in my formula, which will be 8 square 8m, directly I'm taking 4 pi square here. This will be 3n 2 by 3. 3 pi square n 2 by 3. When we put the values, and n will be, we know, sodium atom in BCC, total number of atom is 1 is there in the center, and 8 atoms are there on the corners, but they are only contributing 1/8. So in total, all the corner atoms are contributing in total 1, and then there is 1 in the center of the body. So only 2 atoms are there. 2 atoms, and divided by the volume, which will be A cube, and we can find out from here that will be the numbered electron density. With that all, when I will substitute here, I will get the final answer of Fermi energy after converting it to electron volt. Of course, I will get 3.12 electron volt as the correct answer. Okay, next question is, calculate the de Broglie wavelength associated for an electron in hypothetical metal having energy equal to Fermi energy at 0 Kelvin. Consider number of free electrons per unit volume in the metal is n. So here we know that this de Broglie wavelength means h by Pf, where Pf is the Fermi momentum, h is the Planck's constant, and we know Fermi momentum is h square by 4, 3 by pi multiplied by n to the power 2 by 3. So Pf square will be h by 2, 3 by 2, n to the power 1 by 3. Sorry. It means lambda will be h divided by all this, means 2 to the power, because this will be cancelled, it will be 2 to the power 5 by 3n to the power 1 by 3. This will be lambda, and when you will put the values, this is what we have to find out. This will be the correct answer. We need to do just some rearrangement. Silver is a momentum monovalent metal having FCC crystal structure. If the atomic radius is given, calculate Fermi energy. Again here, this is FCC, same relation we need to find out between A and R. R is given. For FCC, we have atoms touching each other on the face, and face diagonal is root 2A is equal to 4R. So R is given, so we can find out A. A we can find out, then we can find out volume. And for FCC, how many atoms are there inside unit cell? Total 1 from all the corners, then from all the faces, total 3. That means 4 atoms. So number density is 4 divided by volume. After finding out this, we'll substitute in Fermi energy formula and we'll get the answer. And the answer is actually this. I'm just giving you this because time's up. This is in Joule, and then when you will convert into electron volt, you will get 5.53 electron volt. This. And more question. Density of free electron state in 2D solid with dimension A by A, how will it vary? Oh, this is density of state question. We already discussed this several times. We don't need to derive it now. For 2D, we had seen that density of state is irrespective of the energy. So it's a constant for 2D. This is the correct answer. We don't need to derive here again. Okay. So yeah, so these were the problems relevant that I found for this week's topic. The derivations you can go through from the lecture videos, and other things I tried explaining how we see origin of energy bands in solids by considering this kind of model. And although for free electron, E versus K graph will look like a parabola, but when the electron starts becoming localized, then the energy level become discrete and are not continuous anymore. Because of that, we start seeing distortions in this continuity. I was not able to draw here because some problem in my digital pen. I could not draw them properly, but so some distortion starts happening, and because of that we get these bunch of energies that we call energy band, and gap in these energy levels that we call forbidden energy gap. And this way of representing energy bands is called flat band diagram, and this whole thing is called expanded zone scheme. This is one way of understanding, and then further, to actually get the number of levels, we imply the chronic penny model. Derivation again is there in this week's lecture video, so please go through them. And if there's no question, then I'll stop and see you next week. Thank you. Stop the recording.